China is building forests where rain barely shows up and keeping them alive with machines powered by the same sun that used to kill every seedling. Along the edges of deserts like the Taklamakan and the Gobi, engineers are pairing mile-long solar fields with groundwater pumps and drip lines, creating green belts that act like living infrastructure. But the paradox is still hard to ignore. Trees don't survive on sand, and deserts don't offer rivers, reservoirs, or reliable grid power. So how do you turn sunlight into pressurized water, deliver it drop by drop, and keep the whole system running through dust storms and long nights? Stay with man-made marvels as we break down the three core systems: solar, photovoltaic pumping, precision drip distribution, and firm energy support that keeps the loop stable. The first enemy is motion. In drifting deserts, dunes don't sit still. They migrate under persistent winds, piling onto roads, burying channels, and sanding down anything exposed. When wind speeds climb, fine particles lift and travel as dust plumes that can spread far beyond the desert edge. For downwind cities, that becomes an air quality event. For engineers on the desert margin, it becomes a design constraint. Anything above ground gets abraded, clogged, or buried. The second enemy is water physics. In parts of northwest China, annual rainfall can be under 4 inches. Summer heat drives evaporation hard, and on open sand, the top layer dries fast, leaving roots stranded. Even when water is available, the desert doesn't hold it well. Sand doesn't hold water well. Water either soaks too deep for roots to reach, or it evaporates off the surface. So engineers have to deliver water exactly where the roots are. Then there is energy. These projects sit far from dense load centers, and the grid is not always built for running pumps in remote corridors. The grid is far away and not designed for this kind of steady demand. That matters because irrigation can't wait. If seedlings miss their watering schedule in peak heat, they can die fast. This is why just plant more trees fails. Without wind reduction, moisture control, and dependable pumping, planting becomes a numbers game where survival rates collapse after the first extreme season. The turning point is when sand control gets treated like infrastructure, combine land management with an energy plant, then use that energy to run the water system that keeps vegetation alive long enough to stabilize the surface. So the closed loop begins with the first building block: solar electricity that can be turned into water on demand in the same place the trees are planted. A desert solar field is not just a power station. In this context, it is also a surface treatment. Rows of photovoltaic panels block direct sunlight from hitting the sand, cutting surface temperatures underneath. That shaded strip becomes a microclimate zone where early vegetation has a better chance, especially when paired with irrigation. The electrical chain starts at the panels. PV modules generate DC electricity, which feeds into inverters that convert it to AC for standard motor-driven pumps. Control systems watch the sun. When it's bright, they turn the pumps up. When clouds or dust block the light, they slow down to protect the motors and keep water pressure steady. The pumping itself usually comes from wells, because deserts rarely offer surface water where these green belts are built. In some corridors, wells exceed 330 feet deep. Lifting water that far is an energy problem first, and a plumbing problem second. The pump must overcome static head, friction losses in long pipelines, and pressure requirements for downstream filtration and drip systems. Because PV output fluctuates, reliability is engineered, not assumed. If a pump trips mid-cycle because output drops fast, voltage sags, or controls lose stable pressure, the seedlings at the end of the line miss their watering window. In peak heat, that can turn into a rapid die-off event, where mortality spikes in a matter of days instead of weeks. One approach is battery storage, sized to smooth fast changes and extend pumping into the late afternoon and early evening. Another approach is hybrid dispatch. Run pumps hard when PV is strong, then feed storage tanks that act as hydraulic batteries. In practice, many systems use both ideas: electrical storage for stability and water storage for volume. Once water is lifted, it moves through buried mains. Exposed pipes get too hot, crack, and get sandblasted by wind. Buried pipes stay cooler and safer. But buried pipes create a new problem. Water pressure drops over long distances, so engineers add booster pumps or Split the network into zones with regulating valves to keep the flow even. Filtration is not optional. Groundwater and desert distribution lines carry fine grit that can destroy emitters downstream. So stations often start with sand separators or hydrocyclones that spin out heavy particles, then pass water through screens or disc filters. The goal is simple: protect the smallest openings in the system, because drip emitters can have passages measured in fractions of a millimeter. Dust can cut PV output, and in a system where watts become pumped water, that loss shows up immediately at the tap, so operators monitor performance and keep panels clean. Drip irrigation is what makes the water budget workable. Instead of wetting the whole surface, it targets the root zone, letting solar pumping scale without turning into an uncontrolled draw on groundwater. At the nation scale, this connects to what some call a solar Great Wall: long corridors of PV that generate electricity, slow wind at ground level, and support vegetation beneath and around the arrays. In many countries, desert solar is built mainly for electricity exports. China's twist is using the power plant to bankroll and physically support the land rehabilitation system. But once you can produce water, the next problem is precision. How do you deliver it to seedlings in moving sand without feeding evaporation and without clogging the system that keeps the entire belt alive? Drip irrigation is the part most viewers never see, because the smartest versions are designed to disappear into the sand. The architecture starts with a trunk line leaving the pumping station, then branches into sub-mains, then into laterals that run alongside rows of seedlings. At the end of those laterals sit tiny nozzles that automatically adjust to deliver the same amount of water, whether the ground slopes up or down, or whether they're close to the pump or far away. That pressure control matters because deserts force networks to spread out. If one section gets too much pressure, emitters can blow out. If another section gets too little, the end of the line starves first. So engineers segment the belt into irrigation zones, each one protected by regulators, check valves, and flush points. When the schedule starts, only a subset opens, keeping pump load steady and keeping pressure inside a narrow band. The operating strategy is usually pulse watering. Instead of running for hours, the system runs in short cycles that wet the root zone, then pauses so water moves downward into the soil profile rather than being lost at the surface. Compared with flood-style surface watering, drip delivery can cut evaporative losses by roughly 60% by keeping most of the moisture below the hottest, windiest layer. In more advanced sites, soil moisture probes and simple thresholds decide when the next pulse runs. The goal is not to green the surface. The goal is to train roots to chase a deeper, more stable water layer. Sand is the constant complication. Buried laterals reduce UV damage and keep wind from exposing hoses. But the system still needs flush points and zone-level routines to clear sediment after dust events. This is why filtration upstream is paired with flushing downstream. One protects the emitter passages, the other clears what still sneaks through. Now add the second energy system: heliostat mirrors and thermal storage. Photovoltaics are strongest in bright sun, but pumping and control loads do not stop at sunset, and dust can cut output when vegetation still needs water on schedule. A solar power tower fills that gap by concentrating sunlight onto a receiver, heating molten salt for storage, then using that heat to generate steam and electricity later. In an integrated design, PV handles high-volume daytime pumping. The tower extends usable power into off-sun hours and improves stability for critical loads when timing matters. When these systems run together, the impact is physical. Corridors that used to drift now hold their shape. Roads and farms near the desert edge spend less time getting buried, and downwind communities face fewer severe dust events. Seedling survival improves because water arrives on schedule, not when a truck can make the trip. But the trade-offs are real. Pumping groundwater at scale raises drawdown risks, and long-term success depends on monitoring water tables and matching species to local conditions. Monoculture belts can also fail fast when disease or pests arrive. And even with storage, remote projects still face grid constraints if they want to export power. So should desert control prioritize tree counts or resilient native mosaics built around energy and water infrastructure? Share your thoughts in the comments and stay tuned for more stories of innovation and discovery.